Another area which is actually quite important in artificial intelligence is that of simulation. And the role of simulation at place in AI today should not really be overlooked. So what we actually see here in this image are a three-dimensional representation of a specific patient's arteries. And a company called HeartFlow saw this kind of opportunity a few years back. It's a multi-billion-dollar company, I believe, right now. And what they did is they took the CAT scans and using those CAT scans from hospitals where patients were actually going to understand whether they need a heart operation or not. And they converted a three-dimensional model of the patient's heart with all the pressures being simulated with computational fluid dynamics based on this three-dimensional model. And that kind of insight helps quite a bit the doctors who want to make a decision as to whether this patient needs to have a stent procedure right away or some other kind of intervention. So in many instances, simulation is being used not to therefore design the AI algorithms, but to provide world models for those algorithms to be able to provide some kind of augmented intelligence into fields that we are either unable to perform actually physical modeling, for example, designing self-driving kind of cars and all these kind of algorithms that are involved. It's almost impossible to do it by crashing cars all the time. So you have to have a very accurate simulated environments. Here we actually see a different scenario where the simulator is in fact the product. A few words now on how we actually make progress in this field. And in this kind of diagram, what we try to represent is really three axes here. The first axis is this kind of neuroscience and psychology axis, and this represents tens of years of research in this kind of domain, anything from functional decomposition of the brain, trying to get how the brain trying to understand how the brain works, which is obviously a very difficult kind of task. But certain point discoveries have been modeled in what we call now the methods kind of axis over the years, specifically after the reintroduction of neural networks in around 2010 kind of time frame with deep networks present there in many of the tasks. And also discoveries that have happened over there over the years, such as the fact that neurons that are sort of processing our vision are firing locally. They have led to certain models that we call actually here methods in this axis. So a lot of researchers are actually picking up ideas from this axis and they are modeling, providing abstractions into this axis. Even take, for example, the neuron. The neuron is a very complicated organism in reality, but it was modeled in a fairly simple kind of block diagram of, let's say, a dot product followed by nonlinearity, as we will see. Similar kind of modeling approaches of trying to get, let's say, some model of episodic memory or working memory already are present in this kind of domain that we call machine learning and artificial intelligence methods. So the course will be heavy on this kind of axis, but at the same time, no progress will have been made unless we invest quite a bit on frameworks and platforms. And we have frameworks that are software frameworks and hardware frameworks. And in the hardware side, companies such as NVIDIA, AMD, Intel, and others that are nowadays building application-specific ICs to handle the computational workload of machine learning and AI are very much active in this kind of axis. Software frameworks such as TensorFlow, Keras, PyTorch, JAX, and many others have sort of appeared to allow these hardware machines to be able to be fully utilized. And so in this kind of course, we will definitely experience such frameworks, and we'll be using in some instances graphical processing units, GPUs, which are available in the cloud for us. So if I am to map the coarse kind of intersection in this kind of diagram, that's definitely this kind of a green space over there that we will be acting on and trying to understand what really are the methods that we should be using for a specific task and how we're going to go about implementing them. Obviously, there are far more than 4 approaches to AI. These are just categories of approaches and lots of combinations that can actually happen between those. And recently we have seen quite a lot of progress in combining, for example, neurosymbolic reasoning. So the 4 approaches are presented here: the sort of Turing test or test-driven approach, the cognitive model approach, the syllogism, and the rational agent approach are treated here as indicative categories, and we should all be critical that at the end of the day, there's not just a single silver bullet that can actually provide a solution to general AI. In the Turing test approach, we have a machine behind the scenes, and unknown to human, we converse with the machine. If the human is persuaded that's not the machine, then we can claim that the machine passed the Turing test. And there have been various kind of attempts to define, if you like, prices along this. Here you see a couple of videos along those lines on, for example, the Amazon Alexa price, and there are many of others. The capabilities that we need to have to pass the Turing test is obviously be able to converse in a natural language, to be able to devise reasoning, and to to create analogies, to be able to recognize objects and to understand scenes, to be able also to move and interact with other agents like humans are. So lots of progress in robotics, in actuators, sensing, and so on. So initially the Turing machine has started with a just conversational kind of a chatbot type of agents, but then has expanded into other domains that are appropriate for ego motion kind of agents. So the approach that actually I want to stay a little bit on is the so-called cognitive model approach. And along this, I wanted to just show you a couple of objects that I have brought over here. So these are, let's say, 2 objects that are, let's say, present in the scene: a pyramid and a cylinder. And I want to kind of start by asking the following question. If you are asked the following question, you know, what object is on the left of the pyramid? So how about going sort of trying to come up with a reasonable answer the moment you have a scene like this? Okay, and definitely, I mean, the first step is to recognize the entities that are present in this kind of naturally sort of posed question. In order for us to be able to understand, if you like, scenes, we have to build a world model of the scene that we have, we are facing. So I'm just going to go ahead and define a coordinate system. Let's the coordinate system be defined here at the top corner of this pad. So this could be sort of south, and this will be, or maybe instead of south, let me just call it let's say X and Y axes. And we also have a Z axis, although the experiment is not supposed to be 3-dimensional. All right, so we have a 0, 0 coordinate over here. And the first thing I think we should happen every time you're facing a scene like this, let me put it this object this way, is to recognize the location of objects and what those objects are. So definitely we are going to be involved into recognizing objects. So in other words, to put a kind of a bounding box around each object and to be able to detect it and claim that yes, this object is located in this centroid. This is the centroid where the object is located. And this object is actually called a pyramid. And we are certain, let's say, with 95% probability that that's the object, that it is there. And the same thing we actually will do with the, let me put it a bit further. And this is a cylinder. And we are like 80% certain that this will be a cylinder. Okay, so these are the first, if you like, perception subsystem. It should be invoked to give us, if you like, some centroids where these kind of objects are located. And the second thing is that we have to establish via the coordinate system some relations between objects. In other words, we have to interpret the left and how we can actually claim that the cylinder is actually on the left of the pyramid. Probably some form of transformation needs to happen that will connect coordinates of centroids and predicates such as left, from, etc. So all of this kind of a question, it is definitely answerable with kind of today's kind of technology. What we just discussed over here, we actually built a simple model of the world. The world is, this plane over here and this kind of two objects that are, we are able to actually get some answers from that kind of world by invoking several subsystems that we will be designing. In fact, there are sort of in the space of VQA, or let me write this down, see visual querying and answer, or the domain called VQA in artificial intelligence for tooling that will help us answer this type of questions. One of them is called relational networks, RNs. And we have, if you like, a project on the course side that actually deals with this, specifically even using this kind of primitive objects in a scene to come up with this kind of answers. What we actually have developed here is some form of primitive form of a cognitive model of the world. This is what the cognitive model approach invokes and entails. So back to the kind of site, we have looked at some kind of a primitive version of that. Another approach that we have in AI is a so-called logical approach, or symbolism type of approach. In this approach, if I go back to that kind of earlier kind of scene that we had with cognitive kind of model, we see exactly this kind of objects. And in this specific case, our perception system will definitely need to do something more. Not only just be able to detect the objects, but also to determine whether these kind of objects are unique in a coordinate system that we have here. And uniqueness can be determined by some form of localization constraints. And what should happen is that each one of those kind of objects will be assigned a kind of a globally unique ID. In other words, we'll be treating each of these objects like a symbol. That kind of symbol may be associated with some grid world. This grid world is could be expanded all over the plane over here, but here we see just 3 locations in this grid world. Let's say we have location 1,1, location L12, and location N13, where this is the first cell on this axis, and this is 1, 2, 3 cells, 3 coordinates on this other axis, on the axis Y. And with a symbolic kind of representations, what I actually can see is you can assign some propositional kind of symbols, such as P, and we can actually for pyramid, and we can qualify it with, if you like, the location, and we can assign some form of a true or false statement for this. The same thing we actually can do here for the sorry, this is not P, this is C for cylinder, and the location for P is 1,3, that's true. And so this now becomes symbols that are present and in a kind of a symbolic representation, and they can be involved in as sentences in knowledge bases. In our knowledge base, we can actually, using our knowledge base, we will learn in another video how we can make logical inferences regarding relationships between those symbols. And so that is the other approach of sort of dealing with AI problems, the syllogism kind of based approach. And finally, what we have is probably the one that we will be spending quite a lot of time, is the so-called rational agent approach. And in the rational agent approach, we have an agent that finally at the end of the day will need to satisfy an objective. And that objective sometimes is called utility function, sometimes we'll meet it as value functions, or for value functions about its state or its actions that they actually took. So in the rational kind of agent approach, we're always going to have to solve an optimization problem, and the agent is going to sort of move and act in this kind of environment in this kind of optimal way. So that is the rational agent, and we have a whole utility theory behind it that we will get to be exposed in some parts of this course.